The experiment performed is the Cantilever Beam experiment. The object of this experiment is to analyze the vibrations of the cantilever beam due to a base excitation. The shaker excites the beam in a lateral motion, causing mode shapes to appear at specific frequencies. For the equipment used, we have the beam and the shaker, the Doppler effect laser vibrometer, which tracks the movement of the beam, the amplifier, which amplifies the signal, the accelerometer, which measures the response of the beam, the oscilloscope, which records the signal from that accelerometer. Here is the signal chain of the experiment. The function generator sends a signal to the amplifier, which causes the shaker to vibrate. The vibrations of the beam are captured by the camera, as well as by the accelerometer. The data was recorded on the computer for analysis. Verifying the measurements given by the equipment required a mathematical model to be derived. The model was created using elements and boundary conditions based on the Euler-Bernoulli beam bending theory for a cantilever beam. The material properties and the physical dimensions of the beam were used for the calculations of its equivalent spring stiffness. By using this equation, the first three natural frequencies or mode frequencies were found. This derivation resulted in a modal shape equation as a function of the shaker frequency. Combining the modes with this shape function gave the lateral displacement of the beam along its length as a response to the excitation caused by the shaker. The resulting shapes can be seen in the following plots. These plots show the physical shape of the beam at each of the first three modal frequencies. These are ideal animations of the mode shapes. These are computed using finite element method software, COMSOL. Here is an animation of our actual data using MATLAB. At the first natural frequency, the location of the only node is at the base of the beam. As a result, the rest of the beam vibrates around the opposite end. This is actual footage of the first mode shape. At the second natural frequency, a second node becomes visible. The beam is now stationary at two different locations, and you can see the beam vibrating about these 2 points. Here is actual footage of the second mode shape. You can clearly see the node point. At the third natural frequency, analytical analysis tells us that a third node should appear, but the frequency is too fast for the human eye to follow. However, in our actual data, we can clearly see this mode shape. Comparing the theoretical data to the actual data yields similar results. The experimental values to the theoretical values are 12.6 Hz to 13.8 Hz, 80.5 Hz to 86.5 Hz, and 242 to 242 Hz for the first three modal frequencies respectively. Possible sources of error may come from the properties of the beam. The cross-sectional area of the beam may not be constant throughout its length. It also is most likely not pure aluminum. Furthermore, the boundary conditions are not ideal, as this is a real-world experiment. When doing the analytical calculations, it shows a small change in these values produces a significant change in the modal frequencies.